You should get a pop-up on your screen. You have to accept as you go forward. And that way we'll actually be able to have this after the fact. So I appreciate that. I do ask that for all the participants, even those that are from our team, to mute if you can, until or unless there needs to be a question or an answer that you're providing. Just makes it a little bit easier. Don't hesitate to, at any time, put questions into the chat. This particular session is going to be broken into sort of two sections. One is a very brief introduction, which I will give, and then I'll get out of the way to let the experts, which are the students, actually go through an installation and a run, which is the point. At any point after that, don't hesitate to either raise your hand or put questions in the chat. What my job is to try to moderate your questions and make sure they're inserted in and they can be answered by the students as we're walking through. And again, this is going to be recorded, so you'll be able to go back, hopefully, and look through what it is that happened that was communicated at the time. There are also, the students are going to put into the chat itself links for you to be able to download software or download documents as we go forward. So this is meant to be much more interactive than the previous one. The previous one was just communicating outward. This one is also communicating outward, but we also want to make sure we're answering as many questions as we can during this time frame. This session is 2 hours. It's set for 2 hours. The idea was to make sure we had enough time to actually walk through and go through a setup in terms of the simulation environment that you all would hopefully be stepping into. So with that, I will make sure there aren't any larger logistic issues that we have to answer or raise. Garrett, Jose, Tan, anything else? I think that's good. You'll introduce logistics relative to what they're supposed to do once you start your sessions. Okay, very cool. So as of right now, I should be sharing the screen. This is, again, a quick introduction to make sure we're sort of grounded in what we're doing. As a reminder, where are we? Who are we? We are the Leapfrog, part of the Pilot ARTEMIS student challenges that came from the Theme 3 Awards back at the end of 2019 into 2020. Seems like a lifetime ago. We've given a previous seminar on what we're doing, but basically the Leapfrog project goals for this particular activity was to take a lander prototype that had been developed at USC, change it such that we can develop competitions around it and run the competitions in the summer. COVID has changed that to somewhat, and so we are actually communicating to you right now in a second webinar as to that change from COVID, which we're now, instead of doing full flight competitions, we're doing a software competition that will be followed by kits that are actually sent to the winners of the software challenge, which is different. I did want to go through an updated timeline. This will all be on the website. It'll all be updated as well. But the one thing we have changed, or there's a number of things we changed, but one of them is we've allowed the signups to stay going until the 7th of May. So basically next Friday is basically what we're trying to get as many teams as possible signed up, and then we'll say, okay, that's it. We are running the simulation webinars that we started on March 28th and was going to go through May 12th. At that time, on May 12th, we'll finalize the teams. We'll notify specifically of their acceptance and their going forward. So basically that week, 5/12 to 5/17, you can see that we're running the webinars. Today's the second one. We still have one more to go in terms of competition metrics on the 12th of May. And then we've made a change, and we're trying to accommodate as many schools as possible in terms of their timing. We've actually run into that ourselves. So we've moved the start of the software challenge from the previous week to the 24th of May. It will still run 4 weeks, and it will end the last week of the second week of June, which is basically June 18th. So that still encompasses 4 weeks. It cuts down the amount of time we would finalize and contact the winners, but we think that's okay. So we will actually do the validations and the scoring, and then get the notifications out to all the winners from the 21st of June until the end of June, which is what we originally planned for. And then we're basically on the same track where we get out vehicle kits in the first couple of weeks of July. And then toward the end of July, beginning of August, we actually run the boot camps to figure out how to put them together. And at that time, we'll run exhibition flights in California. So that's changes the timing. It's here specifically. This will also be updated specifically on the website, so you'll have all this information as we go forward. Just to give you an idea, as of today, this morning, these were the current teams that had indicated their registration, or at least their interest. So we've got a reasonable cross-section of universities across the country. Really appreciate it. Very excited about this. Couple of notes. There were a lot of questions that came in, and so I wanted to try to highlight those. Only U.S. universities or institutions can sign up for the possible lander kit. So, but international participation or participation from other schools that want to join with a U.S. team are absolutely possible and encouraged. But we really need that U.S. team and a U.S. university to be the lead, because only lander kits will be sent to those universities when we get done with the competition. The other thing to remind everyone is that every team really should have not just a student lead, but really must have a faculty mentor to please sign up. So if you haven't gone out and found one yet, go out and grab a professor or a faculty person and say, hey, we got this cool thing we want you to be a mentor for when we sign up. So really appreciate that. Any other questions about sort of details and programmatics, please put them into the chat. I'll answer them sort of offline. Today is really meant to sort of focus on the software and the presentation. Just a quick reminder, the competition challenge and the exhibition flights. This is basically what we talked about. This is our schedule. March to June is the software challenge. June to August is the building of the kits and a flight exhibition. The one thing that may change that we're still trying to work out is the idea was the top 6 teams get an advance and get a hardware kit to actually build. And the top 3, we would take the algorithms that you created and actually put onto the vehicle to fly. We may have more kits available to the competition team. So, please, we're encouraging everybody to sign up. I'd love to be able to give kits to everybody. Not quite sure we're going to be able to do that, but we may have more than 6. So that's actually pretty cool. Nothing's changed in terms of the boot camp. So the flight exhibition, we're still going to follow that process. Quick reminder, what is Leapfrog? It's this crazy thing that was put together at USC years ago. It uses a jet turbine engine in the middle of it to take off gravity, all self-contained, space-qualified paintball tanks to allow for attitude control systems. And it's been lucky enough that we've actually flown twice, which was great. It's meant to be specifically a hands-on flight test platform for students. We're following that and trying to open this up to the rest of the country. We did do modifications both for safety and ease of operation. So the previous Leapfrog vehicle is going to look a lot different than the one that we have today, which is good. I won't go into that today. I will give you a quick update. We did do, since the last time we've talked to everybody, we finally got to the point that we'd actually take out the base core of the vehicle with the jet engine and the attitude control system and the avionics. And we did a first integrated wireless control startup and idle of the jet engine, validated the ACS valve operation during the engine operations, and then we also validated the initial data acquisition system, which is pretty important. So the cool thing is that this is all pointing to getting us ready to do those exhibition flights. I've got some videos of the hot fire as we need it. So we have some time at the end of this, then I'll probably share that, but I did want to maintain focus to allow the students to sort of give the input in terms of the software simulation challenge. The good news is we are moving forward. Hardware is being tested. Flames are coming out. No, I'm just kidding. But we're actually generating, taking the steps to actually do the hardware and the loop testing to validate everything prior to flight. You've seen this before. I just put this in as a reference. This is also in the previous presentation, but in essence, what we're doing is we're merging a piece of hardware, which is a PixHawk controller, with software on board the vehicle that allows us to run the software simulation challenge in such a way that we would be able to take the algorithms from the simulation challenge and actually fly them on the vehicle, and that there's synergy between the two. So really that's sort of the key point. All of this hardware is in. We're actually doing testing on it as we speak. So again, we're doing the software challenge in parallel with the hardware that's actually going to use what you're developing. This is the thing, I won't go into details with this. This is the thing that Garrett and Andrew and Jose are going to go through today. But basically the entire simulation software, we gave the presentation for the first webinar was what are the particular simulation tools that you could use. And today Garrett and company are going to explain and sort of show how it actually works. We are going to send out a GitHub site. The recommendation is that you actually sign up under your team if you can for a GitHub account. That way it will automatically be able to connect you once you have that account, and we've set up the particular GitHub site ourselves. That's the way that you'll transmit the code back and forth to us, and then we know exactly where you're at, and we can run your code when it comes in to actually go through the challenge. Again, the website is up. We're trying to do as much updates as we can as quickly as possible. Big shout out to Shreya, who's been honchoing that, trying to make sure it works across all platforms. All the information that's going to be presented today will be put onto the website probably by the weekend and up and running again by Monday. So that's the place to go to sort of get the latest and greatest. The registration page is live and active, and like I said, we extended our signups until next Friday, May 7th. If you know another group or another team, or there's a team who's interested today that hasn't been on before, please go ahead and sign up. For those that would like to join with a team, please send me an email to the leapfrog@usc.edu. And I will send an email out. I'll send an email blast out to all the teams to say who might want to join with a university or an academic institution that is not in the US, but still would like to participate. So that'll be the way that I'll try to link it. Again, we're moving fast here. Don't have an automated system to do it, so it's going to be sort of putting you together manually and directly. In case there's any other issues or questions, I've given you both my contact information as well as the programmatic contact for our current activities. So with that, what I'd like to do is stop, and I will hand over to Garrett to sort of take the next step to go through the particular details that we want to share today. Before we do that, is there any top level questions? Are folks hearing okay? Hopefully everything's working out right. One quick question in the chat. The answer is yes. International students can join. Again, there must be a US team or a US university that's leading, but international students, whether here or outside, can join through that team. Yes. Okay. All right, Garrett, I will hand off to you. I will mute my video so no disturbances, and I'll let you go.
Starting off, Dave, let me share my screen. I'm just going to be sharing my whole desktop because we're going to be jumping around between a few different things here. So to start off, this is the GitHub organization, Circ Leapfrog, where we have all of our actual code. In that actual repository called Leapfrog Simulation, we have a discussions post here. This discussion section is the quickest way to get any feedback about any specific questions or implementations about the actual software challenge or the simulation. You can just like post questions here. I'll get notified. We can immediately respond. I also put the references for both this webinar, the slideshow here, which is going to be this link. You'll all be able to access here. I'm going to send a link to this in the chat so you guys can all actually get access to the slides and follow along with the simulation setup guide that we've made in more detail. This contains step-by-step instructions that will hopefully get you from 0 to 100 and get it running here today. So with that, the main focus for me today is really to just take you from nothing and get to the point of being able to run our entire Leapfrog simulation platform. Walk through installation. Hopefully at the end of this, we're going to be able to actually do a very quick demo, and then we'll go over some like basic configurations and how you can change a few of the different parameters here. Let me know if anyone has trouble accessing these slides or the other in detail documentation. My intention behind the overall point of this recording is that you guys can follow along after the fact or now as I go through this documentation. And it should be as simple as just copying lines from this document and having those lines installed waiting for you. So starting off, everything that we do is recommended to use Ubuntu, specifically Ubuntu 20. The main reason for this is just ROS, PX4, and Gazebo, the main things that we use, just run better on Linux. You can technically run it on Windows. You're just going to have a little more trouble, and you can also run it on Mac, but we don't have as much support for this, so we're just not going to be able to help you as much. If you can't do any of those options, you can always use a VM, which is what I'm actually going to be doing today to hopefully get this running. So I have a VM prepared that is essentially completely empty, and then I'm going to go through the process of what you guys would possibly be doing of just copying these lines that I have here and hopefully getting this stuff up and going.
That's good.
I'm gonna
yeah, so nice. At least everything's okay. that was the big thing. So
Hey guys, if you're not talking, if you could mute, thanks very much.
my apologies.
No worries here. All right, so I'm literally just going to be copying lines from here into the VM to run it, just to show how things are going to be working. Unfortunately, because like I'm installing things as like you guys would in the demo, sometimes we're just going to have to wait for things to install. Starting off with the system things, there's some basic packages that are just necessary for everything we do. Git is pretty important, some build tools, CMake, curlmake, and then Python stuff as well. It might be hard to read some of the text here, so it might be useful for if you guys follow along. I kind of need to have this open so I can just copy the commands. In this actual slide deck though, I included all the important links where you can get more information about the actual installation we're doing, and also so you know that I'm not just telling you to install random things. A lot of these are just straight from other sources of documentation that we've then consolidated here. So this script here that I'm now just copying is a script to install Gazebo. That's the main simulation environment we use. This script is straight from the actual documentation. So I'm going to run that in one tab. Plot Juggler is the main visualization software that you can use to actually like view different parameters of the vehicle as it's flying. It allows you to do it in both real time as you're doing the test, and you can view the logs after and plot them in here. If you guys are familiar with Snap Package Manager, it's installed by default on Ubuntu, which is one of the reasons why we wanted to use Ubuntu for this. So if I can just copy this and also install that. And I will type.
Yeah, just be specific on each action that you're doing.
Yeah.
Yeah.
Yeah, for sure. So yeah, on this tab here, we're still just waiting for Gazebo to install. The next thing we're doing is installing Plot Juggler, which is the visualization tool. So right now I'm trying to install both at the same time because they do independent things, so they don't really collide with each other. I put some pretty useful links here for documentation about Plot Juggler itself. So if you guys want to learn more about how to actually use it and how to integrate with it, those are really helpful to check out there. And yeah, once again, if anyone is following along right now and have any trouble in any of these steps, you can let me know now, or you can also post on the actual discussion board that we have, and then we'll post whatever answers we have there.
How long does it take to normally install Gazebo or Plot Juggler?
So Gazebo is one of the larger things. It'll probably take a few minutes. It's running a little bit slower because I have Zoom on right now. In total, if you go through this whole setup guide, just like the process of copying and pasting and waiting for stuff to download, that'll probably take about half an hour. So yeah, both of those things are now installed. Gazebo itself is a pretty large application, which is why it takes a little bit longer to install. Some of the others are a little bit smaller, but then in a bit we'll see ones that are actually much bigger. All right, so we got Gazebo installed, which again, the simulation environment that we need to use. We got Plot Juggler installed, which is the visualization tool to actually view logs. The next step we have is Q ground control, which is like a ground control station software to allow us to interact with PX4. All the instructions I have here are consolidated from the documentation for it. You should just have to copy all these 3 lines. It'll do some setup things that'll allow Q ground control to run. The actual application is hosted at this website that I have here. You can either click on the link and download it there, or you can just copy this whole command. And then this will just download the actual Q ground control application itself. The application is a .app image file, which by default isn't actually like runnable. So you have to make it executable by either copying these commands or running the change mod command and then running it as an executable. In Ubuntu, you can also just go to the files folder, you can right click on it, go to properties here. The main point of doing all these things is that we want to actually change the permissions of the file to make it runnable. So you go to the permissions section, and then there's a checkbox for execute, which then allows us to get it to actually run. So then now, like to actually run it, you can just like double click it. And then this is Q ground control. By default, you have to set your parameters of your units. Just gonna leave it as the defaults for now, and yeah, this is what Q ground control looks like. Once it's actually connected to the rest of the system, it'll usually automatically connect, and then it'll actually like localize on wherever the vehicle is positioned. Right now, it's not connected to anything, so it's just a world view. All right. So we got Q ground control installed. And now the next big step is installing ROS. So the instructions I have here are straight from the ROS wiki documentation for how to install it on Ubuntu. Since we're using Ubuntu 20, it's recommended to use ROS Noetic with Ubuntu 20. So all of these instructions are just straight from the documentation, and you should just have to copy and paste all these commands to eventually do this. So I'll try to explain what these are actually doing as I'm copying them over. In Ubuntu, ROS isn't included as a default package, so you have to add the actual you have to add the actual ROS like instruction file to your Ubuntu system, which is what this command is doing. And then when Ubuntu tries to find packages, you have to authenticate the packages with a key, which is what the second instruction is doing. All right, we're gonna have to fix this. Actually, So I ran into a problem when I just copied this over because this command is on 2 lines right now. It's separating the actual input. So if you get the error that I just got of like this new line expected thing here, then it needs to be a single command where like this long string of characters is actually part of the command. So then it'll actually run and then it'll actually add the keys that are necessary. So yeah, once that's done, we have to update the package list that Ubuntu can see so that it can actually detect the ROS packages. Once it is updated, then we can just install the ROS packages as you would any other Ubuntu package. So this might take a few minutes again, just because ROS itself has a lot of packages.
And Garrett, just to make sure, a lot of these softwares require various libraries. Is everything that you presented so far, all of the up-to-date libraries or separate command files, do they all download at the same time, or do you have to do something separate to your computer to prepare it for these?
No, so all the ones that are in this document is all the latest things that you would need to go from nothing to what we need.
Awesome. Okay.
So yeah, so I'm actually doing this stuff, like this installation in a virtual machine that I just set up for this. So like this virtual machine like has like almost nothing on it. So then what we're installing is just precisely what's necessary to get everything running. And yeah, if anybody runs into any like specific problems or weird things when trying to use these instructions, like the weird thing where like I copied one of these lines and like it didn't work the first try, just like be sure to just drop a question on the discussion board and we can work with that. While we're waiting for this, I'll just talk about ROS a little bit of why we're using it. So the main reason is because there's a lot of different components of our system that all need to run together and all need to be able to talk to each other. So Gazebo is a separate application from our modified version of PX4. So in order to get that communication going, it needs to have an effective communication bus. In addition, when you guys are developing your own navigation algorithms, it can be difficult to integrate this directly into like the PX4 system. So what ROS allows you to do is develop this however you want separately from it. You can use, you have more flexibility in how you design the architecture of your navigation, what languages you can use. And then as long as you communicate over ROS and also MavROS, then that'll allow you to integrate your navigation code that's completely separate with the actual PX4 simulation environment. All right, so ROS seems to be installed here now. The next step here, step number 4, where it's environment setup. This is a very important step that you can't forget. ROS needs to be able to detect itself on your system, and these commands here essentially allow your system to know where ROS is and actually be able to find it when you want to run commands. All right, so we got more packages to install. This next set of building packages is what's going to allow you to actually build essentially the ROS packages. It's kind of weird that these aren't included by default, so it's just something additional that we have to include. And then the final step here is that we have to install MavROS. which is a separate ROS package that allows us to connect px4 and ROS together. And then we talked a little bit more in detail about this at the last webinar. So you guys could check that recording and also like the notes there where we actually go a lot more in detail about what MavROS is and how it works and why it's more necessary. So install MavROS. And then once MavROS is installed, there's a secondary script that we have to download and run, which is provided by these other 2 lines here. I didn't want to actually click on that. I can just highlight this. I'm just going to go back so I can highlight it. So this command literally just like downloads the script, and then the next one following it just runs the script. What we're installing here is a geographic library that allows us to do a bunch of different conversions between latitude, longitude, UTM, and any intermediary coordinate spaces. And without like this library, then you'll find that MavROS will just not run. So you have to make sure to get all 3 of those commands there. All right, so we've installed almost all the prereqs now. The final thing that we actually need is our actual simulation and our actual version of px4. So the main prereqs for that are a few different Python packages, which are included here. These packages are just necessary to actually build px4, and also it includes some of the actual math libraries that are necessary, such as NumPy, which allows you to do some matrix operations with stuff. All right, and now we get to the point of setting up the actual environment. So in ROS, there's usually you usually have to create a ROS workspace where you have all your different packages. So step number 2 here is doing exactly that. We're going to create a workspace called Leapfrog workspace, where we're just going to store all of our different packages. Right now, there's nothing in it, but step 3 is essentially just putting everything inside of it. So we should actually be able to just copy all of this at once. These repos are the repos from our GitHub organization, where you guys will have access to our versions of px4, and this is everything you need to get it to essentially run. So it's very important when you guys do this that you look very closely at what these commands are doing. I'll actually go bigger because it's going to take a second to install. So when we're cloning these repos, you have to make sure to recursively clone them, because the GitHub repo has like sub modules that are in separate GitHub repos, and if you don't do the recursive step in the beginning, then you'll just be missing specific packages for the actual software. You also need to make sure that it's being placed inside of this source directory here. It doesn't matter technically what the name is, but it just has to be inside of the source directory. For the second repo, same thing, you have to make sure it's recursive, so it clones all the necessary extra code. And then the final one is extremely important. When we clone this Leapfrog Mavlink repo, in order for things to communicate correctly, it has to be called Mavlink v2.0. So if you copy this line, then it should be fine, and it should set up all the paths correctly. The reason for this is that we've added custom messages to the mavlink message set. And in order for PX4 and Gazebo to talk to each other and understand our messages, they have to be able to find them. And this is the location that they have to be found at. All right, so check back in. Let's clone this one. So if we now check inside of the source folder, we didn't clone everything. Did we have a problem cloning something? Well, it appears to have some problem downloading it the first time, so I'm just going to copy it. Oh, it says it already exists. Okay, I understand the problem. So on the actual discussion board, I think I'm not going to put this PDF up. I'm going to put a different one up. Once again, I've run into a problem where because this command is on 2 lines, it's not doing the right command. So you have to make sure that this is technically supposed to be a single command that runs on a single line. So essentially what happened is that it cloned these repos into the wrong location. So I have like this. I have these Leapfrog firmware and Leapfrog simulation folders that were cloned correctly. They're just in the wrong place. They should have to be inside of the source directory. So I can just move these into the source directory. So once everything is done, inside of your source directory, you should have this mavlink repo, Leapfrog simulation, and Leapfrog firmware.
And Garrett, just to be specific, on the PowerPoint slide, the SRC alphanumeric should have no space between the recursive. So it's supposed to be all one alphanumeric, or is there a space between recursive and SRC? Because the line, it's 2 lines, right? So it's hard to tell.
Yeah, so there is supposed to be a space between it.
Okay.
I think instead of exporting just a PDF, I'm gonna upload on the discussion board the actual Google Slides version of it that does allow you to just copy it correctly. So when you actually do it like this, there is a tiny space at this endpoint there. So when you copy it from here, it should allow you to actually treat it as like 1 line, and it should work correctly. Okay, so once all 3 of these are installed and cloned, then the final step is really just to build it. So like all of the downloading, all the setup is pretty much done. From here on, it's actually like how do you build the simulation and how do you actually run it. So let's go here. So because we're using ROS in this ROS framework, it's actually, if you guys are familiar with how to build things in ROS, it's the exact same methods here. We're using ROS 1, so there's essentially 2 main tools and 2 main methods to do it. There's catkin and catkin tools. Functionally, they accomplish the same thing, but how you use it is a little bit different, and I'll explain a little bit why you would want to use one or the other, or if you're comfortable with one versus the other. So I'm going to start off with catkin itself. So when you want to run catkin to build, the command you want to use is catkin make isolated. This is a little bit different than the default catkin command. The default is just catkin underscore make. The reason why you have to do make underscore isolated is because of the structure of the actual PX4 framework. Because it's not just supposed to be used for ROS itself, there's a lot of other configurations and other ways of running it. So because of that, in order for it to work correctly with ROS, it has to run in this isolated mode here. So I'm gonna copy that. This command, catkin make isolated, this has to be run inside of this Leapfrog workspace folder here. So you have to make sure that you're inside of this folder. You should just see src folder. And if that's correct, then you should just be able to run this command. And this is probably the longest running command that you'll ever have to do. The very first time that you run it, it has nothing and it hasn't built anything. So it's building from scratch and it'll take a little while. Depending on your system, like I've had it run very slow sometimes and take like 15 minutes. Normally though, it should take like 5-ish minutes. So I'll wait for that. I'll talk about some of this other stuff here. So whenever you build your actual application, you always have to make sure to run this secondary command. If you don't run this command, I'll try to demonstrate it once it's actually built. If you don't run the command, then ROS won't know that that PX4 is actually built, and the simulation just won't be able to be found. This command essentially just tells ROS where you actually built the program and where it can actually run it. The second tool, catkin tools, is a lot more similar to the ROS2 version of the build tool. So if you're familiar with using ROS2 and using that build tool, then catkin tools will be very similar to it. The end goal is going to be the exact same. It'll still build the same application. The main difference in overall commands is that instead of doing catkin make isolated, you run catkin build. So it's a 2-word command versus just an underscore separating it. And instead of doing source devel isolated, this behavior of running packages in an isolated mode is just the default behavior of catkin tools. So then instead of doing source devel isolated, you do source devel. Some additional things just about these tools in general. If we look back at catkin make, it's very explicit about what's happening, and there's a lot to look at and scroll by, which is like both good and bad sometimes. It's very explicit about every single file that's being built and linked together, and any type of error will be immediately printed out and displayed here. So like sometimes debugging your application can be useful, or can be easier when using catkin make. Catkin build by default doesn't have all of this explicit steps in showing every single file that's being built. It's a lot, I want to say, like cleaner, because it hides it abstracts all the stuff away, which can be a bad thing when you're trying to debug. So if you're using catkin build, you sometimes have to be wary about like trying to find your problems. And if you can't find your problems, or you think your debug message isn't being displayed, it's probably just because you need to still enable the debug mode of catkin build. All right, I think this should be the final point for catkin build. So we'll give this a few, and then once it's built, then we'll hopefully be able to run this and everything will come together. All right, so that's good. Actually using the simulation and running it. So this is essentially just a normal ROS package now. And in ROS1, we use the ROS launch command. PX4 is the package that is being called upon, and then we have a specific launch file called mavros_POSIX_CITL, and this is the default launch file that has all the configurations necessary to configure the lander and position it inside of the world, inside a gazebo. So if we just copy this ROS launch command and paste it here, we see it fails because I forgot to copy this line of sourcing after you build. So when you don't source, you get this error of it not being able to actually detect PX4 that was just built. So if we source it now, and then run the ROS launch command, it'll, I might go full screen. It'll essentially launch everything. So it'll launch Gazebo, which we now have here in just a test world. Right now, there's just a ground, there's just a asphalt plane on the ground. If you don't want to look at asphalt, you can see just a normal grid where it can be a little bit easier to view what's actually moving. Each one of these squares is 1 meter by 1 meter. So for reference, like that's what the vehicle size is. So if you guys also want to get more familiar just with like what the actual vehicle looks like and how it functions, you can actually just like go inside a gazebo. You can look at the actual model, the engine, the T-linear actuators that are controlling the movement there. Along the perimeter, we have the different cold gas thrusters to actually control the attitude. And then on the inside, you can see a little bit of how the actual gimbal works. So this is essentially the model. I'm gonna go over how to like use Gazebo a little bit here. So I've been like navigating around this and like manually inspecting it, which is possible for me right now because I launched this environment world as a default mode in paused. So Gazebo allows you to like control the time of the simulation manually. And right now when I'm launching it, it's paused. So if I pressed play, it would like start the simulation, start the physics engine, and try to start simulating things. If you want to actually like do it very slowly, then you can just like step forward one step at a time and view the behavior that way. You can also control the speed of the world to increase or decrease the time if that helps you in your debugging process. The ability to start Gazebo in a paused mode is one of the configurations that are available when you do the actual ROS launch command. So the main ones that are mostly helpful for me when I've developed this stuff is starting at pause and also just not even running like the GUI for it. The Gazebo like GUI that has the actual world and the vehicle is like helpful like for visual inspection, but it also makes things run a lot slower because it's like a very big model that's trying to simulate everything and show everything. But the actual behavior is still just being run on the back end. So if you want to just run this without the GUI, you set the value to false, which you can do with the second command here of ROS launch. Instead of GUI true or GUI : equals true, we do GUI equals : false. And this will essentially just turn off that GUI interface, but still like simulate everything correctly. So you'll still get all the actual values for the actual model, and you'll still be able to interact with the vehicle and interact with the logs separately. Okay, the one thing I think I should still show here is when we run this, we also want to show that we can run to ground control and that it should automatically connect once we start it up. So if we run this, the ROS launch command is the same one I used above and before. I'm gonna minimize this. That doesn't matter. That doesn't matter. And feedback. So I think it's not connecting immediately. So one of the parameters that you need to configure for the actual ROS launch file. I didn't include it in this table. In the actual longer details, earlier when we talked about how ROS needs to communicate with Gazebo and using mav ROS, the way it works is that it essentially tells the communication to listen at a specific port. So right now, I believe key ground control isn't listening at that port. So in key ground control, all of the settings are kind of hidden away in this tab here. If you click on that, go to application settings, then like the settings for actual key ground control pop up. And then this com links tab here or button here is where you can manually set the parameter to connect. So you're going to want to add this. I'm just going to call this px4. Serial connection is if you were actually using the real hardware, then it would be an actual serial connection. For us, the communication over simulation and just in software is actually using a UDP connection. I believe this default port should be fine. And since everything is being run on the same machine, the server address, this is just your local host address, which is 127.0.0.1. We'll press OK, and then we'll hope this connects. And we'll go back, and it says it's disconnected. So now I have become confused. Why does it work immediately? So the port that's used to connect it is configured in the ROS launch file. I might have the default off right now, so I'm just going to show quickly like how you guys would actually change this. I'm just opening up this actual workspace in VS Code so I can just look over the files a little bit better. The launch file that we're using is located inside of this Leapfrog firmware folder, which is the first thing that we clone. Inside of just this folder called launch. So then inside of here, we have this mavros POSIX launch file. That is the one that we were running before. And then the parameter that is incorrect right now is, the default that we were using was 14550, and this is 14540. So I'm just going to change that parameter, save the file. I'm going to go back to ground control to double check that it was the right one. Com links. Disconnect it. I'm just going to delete it and make a new one. A UDP connection at 14550. Add that. Connect to that. And then now when we run this command with this mavros POSIX launch file, this should be the correct UDP port now. And hopefully it connects. And what is document?
Murphy's Law, yeah, when you do things live.
Yeah, it's always the problem of doing live demonstrations. All right, I'm gonna try one more thing before I actually get worried. So at the very end of this presentation, I put all the links to everything that's helpful in terms of documentation here. Let's see if we go to this link, simulation setup instructions. So this is like the more detailed instructions that has more information. Mavros. What am I for here? I need the Mavros PX4 docs. Mavros. Where's PX4? PX4. Oh, PX4. Over here. That was keep ground control, not PX4. Well, PX4 Mavros. Gonna have to switch to. Oh god. For some reason, the PX4 docs doesn't like to load for me on Chrome, so I have to go to Firefox for this to work. And I believe if you go to upload control example. Alright, so what we're gonna do is instead of copying the default parameters that are in the file now, we're gonna use the parameter that they have here. Connect to localhost. So since everything is on the same computer, connect to localhost, and then we're just going to add, actually copy that. We're going to add this to the command. I'm going to disable this one so it connects to the default. So what I'm going to do, I'm going to turn off the GUI because right now we've shown that the GUI works. So we just want to show that it can connect to ground control. So GUI colon equals false. I'm going to paste in this other command, which will hopefully set the ports and URL correctly to connect to ground control. I'm going to run this. And then you're going to watch me do Word, but that just didn't work again. What time is it? 2 o'clock. All right. I have inklings of knowledge of what's wrong with this. Dave, do you want me to actually like solve the problem and go through the process of looking it up, or?
I don't think so. I think it'd probably be better if you do that offline and then you document it and then we'll upload it. Honestly, if we can do another semi webinar to, for folks to walk through this, gotten to this point, and then you can go back in and we can say, here's the solution, so that we can actually do that.
Yeah. Yeah, that's probably a good idea. I'll stop this now.
Yeah, and Dr. Parker also had a good idea that you can check the log file to see if, you know, what might have shown up in there, might have told you. So anyway.
Oh yeah, that'll be helpful.
Okay,
right,
well, so barring running what you had entered, I mean, everything up to this point, this was the last point where it would actually execute. I wonder if you can switch to a running instantiation that you have on another virtual machine or a separate folder and run.
Yeah, give me a second and I can actually run just the one that's on my computer right now. Check that this is running. All right. So this is the version that I have on my computer right now. The main difference is that I have a different version of. Oh wait, I was testing this earlier. So this Leapfrog simulation is the ones that you currently have. This firmware of ours is slightly different because it's more functional. So what I need to do is move the working version of the simulation. Which is, for me, I just call this one simulation, back into the source folder here. I'll do that. I'm using the Catkin tools version of the build tool. So instead of Catkin make, I'm using Catkin build and Catkin clean. So it looks a lot different than the other build tool where it like gives you information about your space. You get this random string parsing error that has like no effect on anything, but like gives you this bunch of garbage. And then yeah, instead of showing you every explicit message, instead like you just get this bar that's saying, oh, 30% complete on one, 60% complete on the other. So the default behavior is to kind of hide away everything that's happening and just like make it nicer to look at essentially. So yeah, since I had to switch out the packages, I have to rebuild it real quick.
So Garrett, this is you trying to transition over to your other.
Yeah, so this isn't in the VM anymore. This is just on my computer.
Yeah. Okay.
Yeah, so what I'm gonna run here is a more stable version of the actual lander with the actual controllers available there. And since it's on my computer, it should also connect to key ground control.
It should. We'll keep that in mind. It should. The key word there. Yeah.
Yeah, that's the hope here. So I think while we're waiting for this to build, I think the probable reason why it didn't connect to key ground control immediately is just because of the way it's installed. Key ground control is using the snap package manager, which by default like installs all the dependencies you ever need to run the application, but it also isolates it from the rest of your system. So it's probably just unable to connect to the rest of the VM system right now. All right, so that appears to have finished building. We get a couple different warnings when you use catkin build. They have no impact, and the last one here is actually just a warning from PX4 itself, and it's just something like they've left in and doesn't really affect anything. So now that it's built, I'm going to source the devel folder, and then I'm going to run this command, which is the same ROS launch command. It's going to start the gazebo. And then it'll say connected. So yeah, once it's connected, it'll just say like ready to fly. I'm gonna clear this mission real quick. So the nice thing about true ground control, if I can make this bigger, is that it makes it really easy to just test things out, to like test out some type of path to fly, or like test out some type of behavior. But it's a very naive way of doing it, of like, if you have no awareness of what your actual surroundings are, kind of just telling it to go to some random points here. And then for all intents and purposes right now, like this vehicle is like in like the Netherlands right now, but in Gazebo, it's just at a random 0, 0 location. I'm gonna clear all this and do a simpler mission. So when you guys design simple missions to actually test your vehicle, there's pretty much 3 main steps you need. So you need to take off. By default, it's going to like 164 feet. I don't know, I'm in feet now. It's like 50 meters. I'm just gonna change this to like 15 feet. So you have takeoff step. You want to tell it to go somewhere, which is just by adding a waypoint. So you click on the waypoint point here, and then you just click where you want to go. I'm just gonna make a box or something, and then you want to tell it to land. So you just press return. It'll do return to launch. And then yeah, once you have a full plan with a takeoff, telling it to go somewhere and landing, then you have to upload it to the actual vehicle. So when it works, it should be pretty fast. It should just say done. I'm gonna go back to the fly. And then now that we have that, we have simple slider, slide to confirm. It'll now try to take off. And then we can watch it try to take off in Gazebo if you want, or you can just like follow along what it's actually doing here. Oh, my return to launch point wasn't the same as the takeoff point. Interesting. But yeah, so like once it's actually like flying, you can just, so if you do the headless mode, then you can kind of just like watch where it's going here, just like if you want like the visual feedback of its behavior. So right now it's still just trying to like take off. It's at like 15 feet, which is the height it was trying to go to. And at some point, it should start to try to go to waypoint 1.
Looks like it's just hovering. Do you have to put a time in order to say go to the next step?
I might have designed my path poorly here. I had a mission start point here, so I'm going to stop this. So like what's happening now is I have a mission start point that's telling me to go to 164 feet, which is what it's still trying to do. And then I have a separate point here to take off, which is confusing it. So normally, I'm going to stop this and upload it back. Let me stop PX4 real quick. Still just hovering. It'll take a while to close sometimes just because there's a lot of things running. Disconnect that. Fly. Connect it first, and then we make the path.
So just while you're doing this, just to sort of clarify, and either Andrew or Jose can identify, you set up the simulation environment, and Q ground control provides an opportunity for you to create a simple profile for the vehicle to fly or execute, but the guidance algorithms are actually embedded inside the PX4. And what Q ground control does is basically provide, here's where we want you to go, or here's where we want the vehicle to go, and it operates based upon basically waypoint navigation modes, but the method by which it gets there, i.e. the thrust vector control or the attitude control, is done under PX4 simulation. And the GNC algorithms that we typically think about, which are the ones that could be optimized, are inside PX4. Is that correct?
Yeah, exactly.
Okay.
All the internal controls that's inside of PX4 in the actual simulation, all Q ground control is doing is this is just providing an interface to take advantage of the algorithms that already exist.
Yep, got it.
So this is like should primarily be used just for like testing purposes, but like very naive testing just to make sure the behavior is like stable. For the actual software challenge, you wouldn't be able to use this because Q ground control has no awareness of like where craters are, like the height of craters or anything like that. So that's where you have to develop some external libraries or packages that do have that guidance algorithms there that you can then directly pass into PX4 and have it take care of that. Let me check this real quick. Okay, so we are here. Takeoff is saying there. That's not right. We're here. Takeoff should be right where the vehicle is. Q ground control again is like convenient because like you can just put points places to make it do something, and it's just like click on it. What I'm trying to do here is making sure that the actual takeoff spot is where the vehicle is, so it knows what to do. So I think that should be fun now. So we have takeoff. We're going to make this pentagon, and then we land. Upload. Plane click. And try again. You sometimes get weird unable to start missions and arming issues when the controllers are like first calibrating or they're unstable. If you have your controllers when you're actually implementing and they're extremely unstable, it just won't be able to arm at all and won't be able to take off because PX4 has like safety checks before it actually moves. That's preventing it from like moving essentially. Okay, so it took off, registered that it took off, got to 15 feet altitude, and then it's now trying to go to waypoint 2, which is also at 15 feet altitude, so it's slowly trying to go there.
And Garrett, just to validate, there's an arrow. Does that conform to a pointing vector on the vehicle, or is that independent?
Yeah, so the arrow here is actually supposed to represent the yaw of the vehicle. Right now, it's still not super calibrated correctly, and it's like rotating as it's moving forward. It's like that's still like a small problem with like our end of like it's getting to the right location while rotating and doing that.
It sort of looks like it's a helicopter that gets there, but okay.
Yeah, it's going a little slow because I think it's just going kind of far.
Okay, and then just to, again, to clarify, what we're looking at is the instantiation of the guidance algorithms that have been programmed into the PX4 applied to a simple stepwise waypoint navigation.
Yeah.
That Q ground control provides. And so really this is just to get an idea, a quick idea of how the GNC algorithms are working in the simulation. Is that right?
Yeah.
Okay.
Yeah. So the actual model we have of the lander is like fundamentally different than like quadcopters and like fixed wing planes that are used with PX4 traditionally. So I guess like part of the main challenge for people is part of the main challenge for us we have to do is like how do we adapt the PX4 guidance algorithms to work with this lander. So we've handled a bunch of that stuff. So at this point, what's necessary to be done is to actually like handle the controls of the vehicle that translates the instructions from internal inside of PX4 that's telling it to go in that direction towards waypoint 2 along some path, and actually sending the commands to the actuators of the vehicle. Yeah, I made it go extremely far because I realized now that this is like a freeway or a road that I'm telling it to cross.
Can you show the gazebo just to see? We can see the vehicle look like it's accelerating in rotation.
Yeah, I think it's actually freaking out right now. That's what's happening.
That's what it looks like.
So one of the things you can do in gazebo is follow it, and it's yawing a lot, which is bad. And it's about to die. That's actually what's happening.
That's what it looks like. Yes.
Yeah. It's gone. I'm gonna stop this. So
that's actually my question was also.
Yeah.
Okay, well, so it's actually the thing is actually showing from the physics and physical what's happening in the vehicle and gazebo, and you can see Q control is indicating where it's going, which also gives you an indication that things are moving correctly. So okay.
Yeah, exactly. I think though one more thing that I want to show real quick is plot juggler, which is what I forgot about. Plot juggler. Plot juggler has these amazing introductory pictures every time you launch it. So plot juggler is designed to work super well with ROS, where once it launches, it'll be able to detect any ROS messages that are being sent. Let me put that on the ground and start it. Q ground controls taking over because it wants to connect. So when you start up plot juggler, since we're using ROS and MavROS and we've already done those connections, these are just some of the messages that are just being sent out from PX4 and are now ROS messages that we can view inside a plot juggler. So I'm going to just select all of these right now to be available. And it didn't like some of those. All right, I'm not going to select all of them. I'm just going to select like a global position. So in plot juggler, you have the ability to just look at the parameters that are being outputted from the actual vehicle and then if you want to like plot them. So this is latitude, longitude. You can just plot the position here. Position in this instance isn't like super useful. This is really just like noise right now. If you look at these axes, like these numbers are all the same. It's just noise. Where this is more useful is when you're actually designing your controllers and trying to tune the vehicle. We've already added some parameters that are available that are going to be like related to the orientation of the vehicle, the roll, pitch, yaw, the actual like linear actuators, like what is actually being applied to them, what is the target values, and what are the current values before it. So when you're trying to tune the vehicle, you could, if you wanted to, you could plot them live. That's not always super helpful because you don't know exactly what you're trying to look at as it's going. So within Q ground control, every time you have a flight, where's logs? Refresh. Every time you instantiate a flight in for the actual vehicle, it'll create some type of log for it. So then, what's April? We'll use this one. So then you can just download the log, and then this log by default is just compatible with Plot Juggler. So if we just download that, then inside of Plot Juggler, if you go to this data section here, these are old logs, which is actually fine to show. So you'll have this .ulg format here. So it's a ulog is what it's called. So these are the default logs from PX4. You can load the data, and now in this instance we have all the Mav-ROS messages that are being outputted, and for post analysis we can actually like look at some of this stuff here. What's a useful thing to look at?
Just show an altitude. That would be good. Just something.
Yeah, there's too many altitude.
Oh.
That's something. You can look at multiple things if you want, but trying to find something that's useful. Local position. So you can like make multiple plots at the same time if you want to show them, if you want to look at multiple things. This was some type of path that it was doing at some point. I don't know exactly which log I just grabbed. So like this is just a position plot when it seems to be very unstable and it's flying around. But I mean, the main gist of it is that you'll just have the ability to use this and then just find the parameters you want to plot and then just look at the behavior here.
Okay.
And then, yeah, I think that's all I really wanted to show with that.
So just to sort of recap here, just a bit. Once you get at the entire simulation environment set up with all the various loads that occur, and you'll go back and figure out why it didn't load to your other virtual world, and we'll post something separate to that. There are sort of three things that allow visual representation and understanding of what's happening to your vehicle while it's flying, and then also to give you post-flight analysis. The first is the gazebo, which you're looking at right here, gives you physics-based instantiation of how the vehicle is flying. You actually saw that. It was actually good that it was unstable because it actually showed that. The Q ground control is a methodology by which you can actually engage and fly the vehicle through some basic pattern that begins to give you some idea about how your navigation algorithms are operating. And it's not so much navigation as it is, do you have a stability in the ACS system, or is your thrust vector control system working well and okay? And so that's cool to sort of see very quickly does it follow the pattern, or in our case, does it start to just completely rotate the yaw a little bit crazy and then go off normal? So that's great. And then finally, one other piece of information, which I actually find really useful and with the students here, is the plot juggler, which allows you to take multiple pieces of data that come from the log file of Q ground control, and then plot it to sort of get an idea of what's happening with the guidance functions. You can actually see what's the commanded attitude versus what's the actual attitude. So you get some idea of the difference between the two. You can actually get an idea of potential latency that's occurring between that. You can get an idea of stability. You can actually plot, in essence, I think you can make a rudimentary guidance stabilization plot. So you can see angles and angular velocity, and you can sort of see, is your state space working correctly relative to a GNC solution that goes into it. So just to validate here, and again, Garrett, what we try to do is to create not just a simulation environment that can run a vehicle that utilizes a model of the Leapfrog vehicle with the appropriate parameters in it of mass, the thrust levels, the thrust of the attitude control system, but also the ability to insert a guidance control algorithm that allows you to tune potentially changing gains if you're using that type of a controller, such that the vehicle's stability, you can test that, you can operate it, you can develop it, and then what the real challenge is not just to take off and be stable and look great, but it's to begin to move and follow a particular pattern. So those are sort of the three tool sets that at least at the moment we've created and utilized. Does that sum up sort of big picture, Garrett, what we're attempting to do here?
Yeah, I think that was a really good summary there.
Okay, yeah. All right. So the one thing that we have not done that you alluded to that I think we have to do, and this may mean we need to have another sort of webinar in between the one on the 12th, is you indicated that when you're actually running the simulation with the vehicle, is the insertion of our world into their simulation. So can you talk briefly about that? Because Q ground control is really just, it's very simple, it's straightforward, it's dealing with it on a two-dimensional fashion, even though you can have an altitude in there, but it's not responding to anything that's in that, we would have hit a bunch of these buildings had this thing really been flying, right?
Yeah.
So.
Yeah, exactly. So what eventually you guys are actually going to have is, instead of just having this rudimentary like asphalt plane, there will actually be like a lunar atmosphere of different craters spread around that actually do have like physical boundaries and different altitudes that you have to navigate around. So what that means functionally for you guys is that you won't be able to use Q ground control to just like tell the vehicle to go to this crater and that crater wherever. You're going to have to use the feedback and use the feedback from the vehicle, which is going to be an actual like laser altimeter that's on the vehicle telling you like how far it is away from the ground. That'll help with the actual guidance here. In addition, we're simulating sensors that like give you feedback and tell you where craters are. By we'll just be feeding to the actual you guys, the teams, the locations of specific craters within some radius of the vehicle. So right now there's nothing here, but if there were just like a random crater somewhere over here, there's a crater right there. Oh, it's in up here. Then like if it's within a certain range, then you'll suddenly be aware of that crater and be able to navigate there. So with that, like that means you can't use Q ground control to do it because you already took off and you're trying to go to there now. I don't know what red lines are.
Yeah, those are supposed to be craters.
Oh, nice. Yeah. Yeah, so like as you're flying, so let's say you took off, you went to this big crater over here because it looked big, you thought it was easy to land to. You suddenly go over, you're suddenly in the crater, and then now you see like some other, because you move somewhere, you're now aware of other craters around you. So then you have to actually send that information and tell PX4 to then navigate to that location.
Well,
So at this point,
let's see. To be specific, go move the world back and leave it where it was. So the challenge in this case that we're trying to instantiate is this is you. That's where you're starting, and we want you to go there, and then potentially to go back over here. So in a very similar to the waypoint navigation mode that you just went in, the question becomes, before you may be able to go straight, but if this crater is actually in the way, you need to understand that when you get close to the crater, and if you look at it from the side, it has altitude to it, right? And you don't want to hit it. So you'll have to be ingesting the altitude. And when you see the altitudes beginning to lower relative to the vehicle, that means that in essence, you're coming up the side of the crater, and we'll put in a particular constraint as an example that we don't want you to get any closer than 4 meters altitude to a crater's edge, that you'll have to respond to that. And there's 2 ways to respond to it. One is you just raise the altitude. The other one is you stop or slow down and you begin to move left or right to understand where that crater is. Because really it's an autonomous feedback system. So if the crater was there, you might have come up here, you would have sensed it, you would have started to move outside until you got back to where you were. But in doing so, the goal is that you remember that you wanted to go here, and that you then turn to go back to that waypoint. All right, so that's the goal. And then the next one is, if you want to get to this one down here, either you go back, or we'll put something in that says that we actually want you to go around the crater and then to be able to go to that waypoint. So you get the goal is to think about and utilize the sensing systems that are available in PX4 to provide feedback, and then you come up with the simple algorithms that provides maintaining the altitude, avoiding an obstacle, and you come up with the algorithm about, do you want to move around the obstacle, do you just want to go up, etc. So that's sort of where we're at in terms of laying out the world. So these craters in Gazebo, what we'll do is we'll actually provide a sample world, if you will, with some craters, and then let you play with that. But the challenge is we are going to change that when you send your code in to us, so that we'll test how well your algorithms work relative to a new world that has craters in a little bit different locations. So yeah, hopefully that works. So awesome. Let's open it up. I know we don't have too many people online. Any questions at this point we might be able to answer that would help from the in our webinar. Okay, I think you can stop sharing, and we'll do a quick sort of roll up here. Right. All right. Well, really appreciate Neil, Sarah, Anish, John, you guys hanging in there. Dr. Park was there, but then he had to left. He sent me a note. Garrett, really appreciate laying this out. I mean, a big shout out to Garrett and Andrew and Jose and Tan, who have been putting the worlds together, or putting all of this stuff together to get out to you guys. Shreya is the one that's sort of writing her on the website, but she also was supporting the competition team, which is basically how we'll attempt to score all these things. This webinar, again, we will, this is being recorded. We'll put this up on the website so anybody can go back to it and sort of run through it. Hopefully you'll have the Zoom, the little, advancing button so you can go past and get to the points that you want to see. And then Garrett will come up with sort of what happened to that virtual world. We'll either post a separate recording that we can point to, or if we think it's appropriate, what we'll do is we'll send out another note so that everybody can participate. But we will have one more of these webinars that will go into the details about the world. So that will be provided to you, as well as the scoring criteria that we've put together. So, all right. once again, we'll open it up. Any questions, any comments from our team, anything that would help the folks online or when they're going to watch this after the fact? Okay. Well, geez, really appreciate it, everybody. This is very exciting. We're excited to support it and share it with as many folks as we possibly can. If you got any questions, don't hesitate to send an email in. We will try to get, I've got to download this video and do all the Zoom. I have to pull it off of Zoom, put it into YouTube, and then get it out. But we'll try to get this in and up with a new instantiation of the website by Monday. So I'll try to move as quickly as I can, but the goal is by Monday that we'll have everything, this as well as everything else up on the website. Under Seminar 2, if you look at the website, you'll see there's a whole section on Seminar 2. Right now, it's just the Zoom link. By Monday, it'll be this recording plus a number of documents that Garen has provided here, as well as the previous presentation. So we'll get all that stuff up as soon as we possibly can. All right. Well, if there's no other questions, I think we will sign off. Really appreciate it. Garrett, thanks very much. Thanks everybody for joining. Really appreciate it. We will talk to you and see you very shortly.